So we get to the idea of an electric field now. So around those charges, what if I was to put some test charge to figure out how the test charge would behave? All right. So we decided, kind of going way back, that the test charge would be a positive test charge. So if I put a positive test charge kind of somewhere over here, so let me go and say, here's Q naught, and it is a positive test charge. How would it behave? Well, it would be attracted to the negative. So based on how it would behave, that particular charge really would have a force on it based on how far it was away from the charge it's near. I could figure out that force, and I could figure out the force on the charge, but I want to cancel that test charge out. So we end up with an electric field being in the idea of force per unit charge. Okay. So we end up with this idea of E being F over Q, where Q is the test charge that I've put it near. All right. Now, if I'm near a negative charge, my field lines go towards it, because obviously, if I was to kind of go over here and put a positive test charge, it wants to go towards it. But if I was to go over here and I put the positive test charge, it wants to go away from it. So they radiate away from the positive charge. So basically, we've defined it based on how would the force be on that positive charge, but then canceling out the value of the charge. So the simplest way to think of it is, again, taking Coulomb's law, which is the KQ1, Q2, is this. It's basically KQ, where the big Q is the Q generating the field, over D squared. So now, this makes us think of electric potential. Some people, the analogy is easiest when we think of it as the same as gravitational potential. So if I start out with gravitational potential, I've lifted some mass to some height. So I've done force times the distance, done work on it. But now if I let go of that object, that force is going to be allowed to go for some distance to do the work again. So now the potential here, instead of being, just force distance, it's K Q1, Q2 over just D, because we've canceled out that extra D from the D squared of force, right? Because technically, if I'm looking at force here, technically that has the whole K Q1, Q2 over D squared. But when I multiply it by D, well, we're left with just K Q1, Q2 over D for electric potential energy. Now you might notice I'm using a U to represent electric potential energy. Well, that's actually a common symbol in physics. Instead of using PE before, I could have used U before. And the reason we use a U is it looks like a well, like a potential well that I could get stuck down. Like, oh no, Timmy fell in the well. That's why they use the U. Another comparison some people like to think of it is with a spring. They could imagine now, what if I had the positive test charge and I had to try to push it towards another positive charge, right? That's like trying to compress a spring. If I then compress the spring and let go of it, bing, it wants to shoot off. It doesn't want to be there. Even though I put work into it, it doesn't really want to be there, so it moves off the other way. So that's another way to kind of view this idea of the K, Q1, Q2 over D. Now, this brings us to this other idea of what's called electric potential or voltage. Okay, so electric potential or voltage is a little different. So electric potential or voltage is like saying, I don't really want to have to care what test charge I just put there to figure out the UE. So the way we just talked about kind of UE as being the whole, force times distance. What we're saying here now is I want to cancel out the test charge that I put in there. So I'm doing the force times distance over Q. That's where this other piece kind of comes in. So I'm canceling out that test charge. So one way to look at it is V is equal to ED, because we know that F over Q is E, the field. The other way is actually just to look at it as FD is UE and say it's UE over Q. And voltage, or electric potential, is in units of volts, which is joules per Coulomb. So examples of this. Well, one thing we're going to talk about is the Van de Graaff generator. So I can have a certain force at a certain distance on a certain charge for the Van de Graaff generator, which is then also caused by a field at the distance or the electric potential energy on that test charge. What's different, though, about electric potential is it doesn't care about the actual test charge. So if I've got twice the energy on twice the charge, or 3 times the energy on 3 times the charge, that factor of 3 cancels out, and it tells me, kind of looking at this here, when I'm at this distance here, it's V, regardless of the charge I have. It doesn't care whether it's a small charge with less, UE, less electric potential energy, or a big charge with more electric potential energy. It's the same electric potential. It's the same voltage at that point. All right. And that's why it really becomes important to understand electric potential. Electric potential is like saying, how does any charge behave at this point, as opposed to how does this specific charge behave, or how much energy does this specific charge have. So it's like basically saying, I'm getting the charge specific piece out of the potential. So it's basically saying a charge will move like this at this point, but not necessarily this fast or this strong or whatever it is, because we've canceled out the actual Q value. Electric potential energy is measured in joules. Electric potential, on the other hand, is basically potential energy per charge, right? So that's joules per Coulomb, which is also known as volts, watts, amps, or it's also joules. And the answer is volts. So just to remind you, 1 volt is equal to 1 joule per Coulomb. High voltage can occur when we have a low electrical potential energy. So that's like the Van de Graaff generator. So I can zap you with a very high voltage little zap, right? Because that bolt can go through the air, which means it has a high voltage, high electric potential. But there's not a lot of energy there, so it's not going to cause any harm. All right? Unlike what we call the high tension lines, right? The high tension power lines. Those are high voltage with high electric potential energy because there's a lot of charge there that wants to move. So there's a lot of electric potential energy. Those will kill you. Both are at 50,000 volts, just Van de Graaff generator is going to zap and tingle a little bit. High tension lines, those are going to kill you. So now we get into the idea of storing electric potential energy. And we do that with something called a capacitor. So we basically take 2 flat plates, and on those 2 flat plates, one gets hooked up to the positive side of an electrical source, one to the negative side of the electrical source, and we cause an electric field to happen between them. And depending on how close those plates are and how big those plates are, there's going to be a difference in how much electric potential energy we can store. The charging process kind of goes through the idea of we have the voltage in the battery, which is our electric potential, okay, the voltage, and then the bigger the plates, or the closer they are, the greater the charge can be stored. They also can discharge very quickly too. So a charge capacitor, if there's nothing to restrict its discharge path, which we'll talk about things like resistors and inductors in future units, can discharge very rapidly, which can be dangerous. That's partially how stun guns work, is that they charge up a very high value capacitor and it discharges very rapidly. It's also how camera flashes work. They charge up a very high value capacitor and they discharge very rapidly. The charge stored in the actual capacitor, Q, is equal to CV, where C is the capacitance value. So Q is going to be in coulombs. This idea of capacitance, C, is in farads, and then V is still in volts. So 1 farad is actually 1 coulomb per volt. Most of the values that we actually deal with are very small. So we're talking about picofarads or microfarads. So picos 10 to the negative 12, micros 10 to the negative 6 farads. And they're in almost all electronic devices you see. Most common thing that people care about them in, that I found, has been computer graphics cards, because that's the number 1 component that fails in computer graphics cards, are these very small capacitors, but as they cycle through, generating images over and over and over again at, 60 hertz or 120 hertz, they finally fail after a while. Now, you can increase the plate size to increase your capacitance, which is like adding capacitors in parallel. So kind of to sketch what that looks like, that would be like if I had this plate here and this plate here, right? And I kind of link them together. So those plates are linked, those plates are linked. That's adding them in parallel. I could also add them in series, which increases the separation between the plates. But if I do that, it decreases the amount of capacitance. So if I do this, going from here to here, that distance has now increased, as opposed to just one capacitor being kind of that little bit there. So I've actually decreased the capacitance because I've given more distance between the plates, the outermost plates. As mentioned before, we're actually storing energy on them. And the electric potential energy stored, the UE, relates to 1/2 the charge times the potential difference V. You can either increase the capacitor's storage by, or electrical storage by increasing the voltage or increasing the Q. But you got to realize Q is related, and V are also related to C. So you can also bring in the idea of Q equals CV into play here, and figure out the electrical potential energy in terms of the actual capacitance value. So just because you want to increase Q doesn't mean you can increase Q, because the capacitor can only store so much charge before it fails, and then kind of left with that piece. Again, we're going to be doing lots of practice with this, lots of problem solving, kind of as we go forward.